Okay, so I'm making this recording just to help you guys out, those who are absent. It's a snow day, so I have time to do this. All the other kids took their quiz. The first, I gave them 15 minutes to do it. They did fine. You guys will do fine too. Just make sure you check your study guide. You'll be fine. All right, let me share this with you. All right, here we go. Okay. Obviously, I need to change that for a second. I thought I had this done. I didn't. There, now it looks beautiful. Okay. So we're a snow day on Wednesday. Don't know what'll happen on Thursday, but if we do come to school on Thursday, we'll do 9 to 5. This is going to be class 9.4B. Here is your homework. Go ahead and pause it. Copy this down. All right, here we go. So this is the conclusion of the first lesson on vectors. Recall that what we learned from last class. So vector, remember, is a mathematical concept that combines two basic ideas. The two basic ideas are a magnitude, or how much of something you have, and a direction. And both of those concepts of both size and direction are combined into one basic idea called a vector. We think about the visually, we think about a vector as having an initial point and a terminal point on the coordinate plane. Initial point meaning the start of it, terminal point meaning the end of it. This is drawn as a ray, although I remember rays go on forever, vectors do not. The initial point is literally a point on the graph. Terminal point is a point on the graph. And we said we can calculate what's called the position vector, and that's the vector that can be placed at the origin by simply taking the x values, subtracting them, taking the y values, subtracting them, and writing them. Now, vectors, when they're drawn as position vector, have this special notation to it. I haven't done this in a while. Let's see, draw. There we go. Annotate's what I want. There we go. So I have these two, it look like greater than, less than symbols. They're not, they're vector symbols. And then secondly, there's this additional way of writing a position vector with an I and J. And I realize it's confusing simply because we already had the class on complex numbers. We use the I for complex numbers as well. This doesn't mean it's a complex number. This one is a vector number. All right. Let me clear this. Clear all my drawings. Okay, here we go. All right. How do we calculate the magnitude? So the magnitude, you get that double, looks like absolute value symbol right there with the V for vector. If you have the position vector, 4i plus 4j, you take the x value, or I should say you take the I value, 4, you square it, you take the j value, 4, you square it, add or sum that together, take the square root. Basically, it's just a Pythagorean theorem, but because it's a position vector based upon one of the points being 0, 0, we lose all that other details of the distance formula, and it's a pretty simple process. So you take the number attached to I, square it, take the number attached to j, square it, add it together, take the square root, and that is the magnitude or the size of your vector. And then lastly, we calculate the direction. And once again, remember, if we draw this on the coordinate plane, the vector itself, we can make a nice little triangle. Therefore, if we want to find its direction, you would have the x and you would have the y. Therefore, inverse tangent would produce that value right there. All right, so that's what we learned in that first part of the lesson. So switch gears, we'll do a couple different things today. Primarily, this is focused upon what are vectors really useful. That's kind of how we'll end the class. So a couple quick examples of vectors that you would see. There's two main ones that we'll see mostly in science class. The first one's called a velocity vector. And if you could imagine, they usually use an airplane. An airplane flying has both a, it has a speed and it has a direction. And together, we combine those together, we call that the velocity vector. So an airplane flying due east at 200 miles an hour, that would be an example of a velocity vector. The second and equally the most common one that you'll see is something called a force vector. So if you're pushing an object, you're pushing it with a specific force, and you're pushing it in a specific direction, and that's what's called the force vector. So you'll see both of those tonight when you do the problems. One deals with movement in the sense of an object going through space and a direction and a speed, and the second one is an object that is moving because of force being applied to it. All right, both velocity vector and force vectors both have the same type. You calculate their position vectors exactly the same way. All right, so let me teach you a new skill. Before, we basically had a visual vector, and that was a vector placed upon the coordinate plane, and we were able to do add, subtract, multiply, and divide with those things. Now, what I'm going to do is I'm going to give you the specific parts of a vector. I'm going to give you its direction, and I'm going to give you its magnitude, and you're going to calculate the vector. So I will tell you that the direction that this thing is going in, I will tell you the magnitude of it, and you're going to come up with the vector itself. This is a pretty slick process. I'll explain it to you real quick. If we, and this is also why it's in the trig section of the pre-calc book. Once again, I'm going to give you its magnitude and its direction. And if we think of that visually as a vector, remember we can yank this vector, lift it up, place it back upon the origin. That would be its position vector right there. Gives us a nice little triangle. And if we think about the unit vector of that, remember the unit vector is you take the two constituent parts, the I and the j, you calculate the magnitude, and then you divide the I and the j, the coefficients of the I and j by its magnitude, and that gives you a unit vector. In other words, it gives you a vector going in the same direction, but it only has a magnitude of 1. We've seen that before. That's basically the unit circle. And therefore, if I know what r is in this case, we're going to call that u, and then I can calculate the x and the y simply by taking the sine and the cosine. We've done this before. We converted a polar to rectangular coordinates. So it turns out for vectors, it's the same basic idea. Notice they didn't put a theta there. They put an alpha. Okay, we can wrap our heads around that. But to calculate it, we simply, or the x and the y portion of it, the I and the j portion of it, we simply take the cosine of alpha. Remember, cosine of theta is equal to the x value and for the unit circle, and the sine of theta is equal to the y value for the unit circle. And since we now have a unit vector, a vector of magnitude 1, it's what applied to the polar to rectangular applies to this as well too. So all we simply do to find the coefficients of I and j is simply take the cosine. Remember, I'm going to give you the direction. We take the cosine of that angle. We take the sine of that angle. That gives me my x and y, or my I and my j in vector speak. And we're done. All right, so let me show you, well, let's write this down first. So it says, if v is a vector with a magnitude of v and a direction of alpha, and we're going to consider it somewhere between 0 and 360, then we can calculate its coordinates by simply taking its magnitude and multiplying it by the cosine of alpha I plus the sine of alpha I. Distribute the magnitude back to the inside. I'll give you a second to write that down, and then we'll do a couple examples. Okay, so I'll show you a quick example. So here's a real world example. Most of the problems tonight will be real world. It says a ball is thrown at a speed of 25 miles an hour. So that's your magnitude. That's your force. I'm sorry, that's your speed vector, or speed portion of the vector. Ball is thrown at a speed of 25 miles per hour in a direction that makes an angle of 30 degrees with the positive x-axis. That's from standard position 0 degrees. So we're 30 degrees off from that. What is its velocity vector? All right, remember, to do a velocity vector, we use the formula. And the formula says take the magnitude and multiply it by the cosine of the angle, and then plus the sine of the angle. All right, so let's think. It also says it's 30 degrees off of the standard position. That's 0 degrees, standard position. So 30 degrees off from that. Remember, we're going to consider that the polar axis, the x value or the I value, and we're 30 degrees off from that. Throw the other part of that, which would be the y, or in this case, the j portion of the vector. And now we can calculate its its position vector, or we're going to call it now the velocity vector, one and the same, by simply using this formula. Now, the red dot I put right there, remember that we're actually calculating that point. So the process is you take the magnitude, you consider this as being a unit circle once we divide out the magnitude, and then when you reapply the magnitude back to the equation. Now, that's when we distribute that v back into, or the magnitude back into this portion that's inside the parentheses. So it's a pretty simple process. All we're going to do is throw in 30 in for alpha, but we do need to calculate the magnitude, or do we? Well, in this case, our life is easier since it tells us what the magnitude is. It tells us the magnitude is 25. So all we really have to do here, this is literally as easy as it gets, is simply look at our unit circle and figure out what the cosine of 30 is. And remember, the cosine of 30 would be the x value. So let's see, for 30 degrees, the cosine would be √3/2, and the sine would be a half. And so all we have to do is take those two values, and remember, when we write vectors, the I and the J are bolded, and simply distribute the 25 to the inside. Boy, it looks like a really ugly answer, and it is an ugly answer, but the process to get to the answer is fairly simple. So back up one more time. You'll be given a problem. It will give you a magnitude, in this case 25. It will give you a direction, in this case 30 degrees. If you visually need to draw this, you can. If you understand what's going on, where they give you the magnitude and they give you the direction, then all you really need is that formula right there in red. Plug in the values. 25 is the magnitude, 30 is the angle. Go to your unit circle, figure out the values for cosine and sine, and then distribute the 25 to the inside. And that literally is the process right there. How will they make it more challenging? They really can't. If they're not giving you the actual position vector, they're doing it the opposite, where they're giving you the magnitude and they're giving you the direction, then it's going to be very clear in the problem what is the magnitude and what is the direction. Generally speaking, in a real world problem, they're going to give you the direction in the form of degrees, not radians, but remember, this can work either way, degrees or radians. All right, and it really is that simple. Even simpler is take away all those words and simply give yourself the actual values that you need. The two values we need are the magnitude and we need a direction. So this is just plain simple, just running through it really quickly. So if they give you the magnitude, in this case 5, they give you the direction 60, and all you're doing is plugging these numbers into this formula right here for the position vector. So the position vector is take the magnitude and multiply it by the quantity of the cosine alpha I plus sine alpha j. So I plug those values in. Now, are they going to give us values that aren't on the unit circle? If they do, then grab your calculator, and it's even easier with a calculator, obviously. Let's see, cosine 60, well, it'll just be the opposite of the 30 degree one. So remember, the 30 degree one goes √3/2, 1/2. So it's just, we're in quadrant 1, goes to 60 degrees. So this one is 1/2 and √3/2. Distribute the 5 to the inside. And okay, once again, it's not a pretty answer, but it is the answer. So we're only going to do 2 of those. They're pretty straightforward. For homework, they'll give you a few of these where they give you the magnitude, they give you the direction, and a few of them where there's words, or there's a scenario, but it'll be obvious what the magnitude and the direction is. Okay, that's concept number 1. Can we do the opposite? Meaning, if I give you the position vector, can you come up with the magnitude and can you come up with the direction? The answer, of course, is yes. So here is the position vector. The vector v is 4i minus 4j. Let's figure out the direction. Okay, so the direction, well, the first thing we have to figure out is what quadrant we're in. So let's see, 4i in terms of rectangular coordinates would be my x value, and minus 4j would be my y. So let's see, my x is positive, my y is negative. Well, that would be what, quadrant 4. So quadrant 4, I'm just going to freehand this. So if I just draw this and put the point where the end of the position vector would lie, that's that blue dot I just drew right there. Is that accurate? Oh, I'm sure it isn't, but it's in the right quadrant. I'm only putting it there so that we can wrap our heads around where it lives. So it lives somewhere in quadrant 4, and our goal here is to figure out the directions. In other words, that alpha that's right there that I just wrote in red. Okay, so how do we do this? Well, remember, it's given us the position vector, so it's saying that the x value or the I value here is 4. So there's my x/I value, and the j value corresponds with the y value, so that would be a -4. If you want to draw a triangle, you can. But the answer to figuring out its direction is always going to be an inverse tangent. Let me see if I can do this real quick with annotation. Now remember, if I made this into a full triangle right here, the -4 would be over here. And so in relationship to alpha, this would be the opposite, and this would be the adjacent. So if we want to solve for, use some trig to solve for the direction, then that would be inverse tangent. All right, makes sense? Okay. All right, so let's do that math. Let's see. So that would be what? Y would be -4/4. That reduces to a -1. And hopefully by now, this number is very familiar with you, -1. We can get a 1 with a 45-degree angle of some sort. Remember, that's √2/2 for both the x and the y values. So a negative, and I mean, I can already tell where it lives in quadrant 4. So it's 45 degrees off of 0 degrees, or if you want to think of an opposite way, it's 45 degrees plus 270 degrees. Remember, 45 degrees is dead smack in the middle. Why? 90 degrees per quadrant. So lots of ways we could write this. We could write this as -45 degrees. We could write this as -π/4 degrees if we want to write it with radians. Let's see, 45 and 270 would be 315. So 315 degrees, and let's see, 315 degrees in radians is 7π/4. We got lots of options there. Pick one, whichever one you like. I'm going to stick to the easy one. Well, actually, -45 would be the easiest one, but I picked 315. All right. And it literally is that simple to find your direction. So the direction, once again, how do we figure it out? We simply, we understand what quadrant we live in. We get that from the position vector itself, where the I corresponds with your x value, your j corresponds with your y value. I figured out which one was positive or negative just simply by looking at the numbers. I figure out what quadrant I live in. I plug in the numbers. And I will just say for direction, it will always be inverse tangent to those values right there. Could you plug this into your calculator? Sure, you could as well too. Just remember, if it wasn't a nice thing like here, for instance, if you were typing in radians, it would give you, when you did inverse tangent, it would give you a decimal value. Wouldn't make much sense because it would be in the terms of radians. But in degrees, yeah, your calculator will spit out, your calculator will actually spit out -45 degrees if you throw that into your calculator. Okay, one more, same thing for direction. All right, so let's see. Step number 1, we look at the two values in our position vector. The I and the j corresponds with the x and the y. Let's see, x is negative and y is positive. So quadrant 1 or quadrant 2. So let's see, that would be quadrant 2 where the x is negative. So I'm going to put a dot right there. That doesn't necessarily mean it's exactly right there. It's just simple. It just stands there so I can visually wrap my head around what's going on. So let's see, the x was negative. I put that alpha there pretty close. And the y is positive. It's always the same thing. It's going to be inverse tangent. Just make sure that when you do your inverse tangent, remember it's y over x, not x over y, that you don't screw up the numbers here. Let's see. X was the -3√3, and the y was +3. Let's see. The 3's would cancel there. Multiply top and bottom by √3. And we've seen this plenty of times. This is either that 30 or that 60-degree one. We simply wrap our heads around what's going on here. For those of you that don't have this memorized, well, it's either going to be 120 or 150. Let's see, I need to have a √3 on the top and not the bottom. And that one's going to be your 150 degrees, or 5π/6, or negative. Let's see, that would be what, -30 degrees off of 180. Lots of different ways of writing this. So you can't, the answer is not -30 degrees, but it's 180 minus 30. So this one would either have to be 150 degrees or 5π/6. And in any other way, if you want to go in the negative direction, you can as well. All right, hopefully that made sense. All right. We can solve problems with vectors. We've seen that before where we combined two vectors, we subtracted two vectors. We're only going to do one of these. This is a short class because of the quiz. Remember, it took up 15 minutes. We're only going to do one of these. I picked the one that probably will cause some confusion. All right, so remember multiple vectors is we take the two vectors, we attach one to the other one through addition, we flip it around for subtraction, we multiply using a scalar, all of those make sense. So probably the best example of why you would do this is, once again, if you have two vectors acting upon an object, the resultant vector, or what happens after you apply the two forces in the two directions, results in where is the object either moving or going to, that sort of thing. And so our basic questions would be, okay, so if I apply two forces to an object, how fast is it now going and in what direction? In other words, what is the resultant vector? And this is why this process is really powerful. And we're not going to do it visually in the sense of lifting one vector and placing on top of the other one and then drawing the resulting vector. We're going to do this all algebraically. All right, so here's the one example that I picked. I picked the airplane one because of the winds. The winds are what usually cause students problems. So the basic scenario is you got a plane flying to the south. South is not 180 degrees. South is 270 degrees. All right, so the plane is flying south at 500 miles an hour, and during the flight, it encounters an 80-mile-an-hour wind coming from 225 degrees or coming from the southwest. 4 questions they ask you: what is the plane's vector? What is the wind's vector? What is the resultant vector? And then finally, the 2 good questions, which is, well, what is the speed of the airplane now as it encounters that wind, and what direction is it going? If you encounter a crosswind in an airplane, you're not going in the direction that your nose is pointed anymore because the wind is pushing you. So this is a really good example of why this technique is powerful once you see it in action. Now, I will warn you, the numbers are really messy and really ugly. It is definitely a calculator problem, but you can see the power of combining vectors in this one problem. The issue with this specific problem, why I chose this one, is because of the winds. All right, so the book has this little picture right here. I have no idea where the plane is taking off from, but right now it's currently flying to the south. If you look at the little airplane right there, it shows 3 airplanes. That's just over time. Its nose is pointed due south. So it's pointed at not 180 degrees, that would be west. It's pointed at 270 degrees. And as the wind, which is coming from the southwest, notice the wind is blowing to the northeast. So 225 degrees, well, 180 degrees off from that would be 45 degrees. The wind is blowing in the direction of 45 degrees. Now, weather people, don't ask me why, they always say where the wind is coming from, not where it's going to. And I guess from a human standpoint, you want to know where, when you're walking, where is the wind coming from, because that's what would be hitting your face if you were walking dead into it. So winds are always given basically in the opposite direction of what you would want for a math problem or a science problem. You want to know where is the wind going towards too, because that's the direction that the wind will push you. Hopefully that made sense. So the wind is coming from 225, but it's going to 45. Now, where did I get that? I got that from taking 225, subtracting 180. So the wind is blowing in the direction of 45 degrees, so northeast. And it's going 80 miles an hour. And that's a pretty strong wind. And when you get a plane altitude, winds are very strong. All right, so we'll just answer these questions one at a time. It says, what's the plane's vector and what is the wind's vector? So let's see, the plane's vector, we need a magnitude, we need a direction. It says south, that's 270. The magnitude is 500. We've already planed this, or we've already done this one a few times. We simply throw those values in. So let's see, the angle would be 270 and the magnitude would be 500. Let's see, cosine of 270, that would be your x value, that would be -1. And for sine, that would be your, I'm sorry, x value would be 0. My apologies. And the sine value, the y value would be -1. I just got those backwards there. All right, so you got a 0 vector or a 0 for the cosine of 270. So when you distribute that 500 to the inside, I'm going to leave that there as a 0i. You don't have to. You could simply write it as minus 500j and it would be fine. I'll just leave it there just for the sake of clarity. So there's your planes vector. Winds vector, once again, this is just a plug and chug thing. The wind's going 80 miles an hour, and the direction, once again, this is where you make your mistake. It's not 225. That's where it's coming from. It's going to 45 degrees. All right, 45 degrees, we're familiar, that's root 2 over 2. So both of those are going to be root 2 over 2. Multiplied by 80, half of 80 is 40. So we get that vector. Now, I called that vector V sub W, the vector of the winds, and I called the airplane one V of A, so the vector for the airplane. Hopefully that makes sense. All right, what's the speed of the plane over the ground? Now, visually, this is what's happening. Visually, this is what's happening. So the plane is trying to fly south. By the way, I'm just drawing this with I don't consider the length of this to be its magnitude. I'm just drawing you basically a visual representation of what's going to happening. So as a plane tries to fly south, the wind pushes it in that direction right there. So the resultant vector would be, well, it doesn't look like we're going south anymore. It looks we're going less than south. So a little bit less than 270, or excuse me, a little bit more than 270 degrees due south. Okay. Well, let's do this. Well, remember, the resultant vector is you take the two vectors, you add them together. Pretty simple to do. So we have our vector of the airplane, we have our vector of the winds. We plug those two values together and we add these? Yes. All right, so this will visually look very intimidating as an answer, but that is the answer. If you wanted to simplify that and write a decimal approximation, you could, but this is the exact answer right here. And exact answers are far better than approximate anyway. Okay, so that's my new resultant vector. But the question doesn't say what is the vector, it says what is the speed of the airplane. Well, the speed of the airplane would be its magnitude. So once again, to find magnitude from the very start of the class, and this was actually from the previous class, to calculate magnitude, you simply square the I value, square the J value, add them together, and take the square root. And you're like, yeah, but look at those numbers. They're really messy. Well, that's what calculators are made for. All right, so to calculate the speed of it, we square the I, we square the J, add them together, take the square root. So, oh boy, look at that thing. This is just to plug it into your calculator, to let your calculator do the heavy lifting here. It results in a speed of about 447 miles. You can confirm that with your calculator there. Be careful with your parentheses when you're doing this, especially that second set of parentheses there. If you leave those off, then it squares the 500 and not the 40 root 2 minus 500. All right. That's 3 questions now. We got 1 question left. What is the direction? Remember, the direction is simply going to be inverse tangent of y over x, and that corresponds to j over I. So let's see. Oh boy, once again, really ugly numbers. You got to be really careful with this one. When you plug these numbers into your calculator, see the y is the quantity 40 root 2 minus 500. And the I value, or your x value, is 40 root 2. Now, I will just say, when you plug this in your calculator, your most common mistake would be you forget to leave off parentheses right here. So I'll put those in there for you. If you leave those off, then it's going to divide the 500 by 40 root 2 and give you definitely a different answer. Okay, so we plug that all into our calculator. It's going to spit out a direction. In this case, your calculator would spit out negative 83 degrees. Well, let's just figure out what quadrant we're in. Well, I mean, you can visually see it. We're going to be in quadrant 4. You can see the airplane there. So we're going to be in quadrant 4. Let's see, 83 degrees off of 360 degrees would be 277. That's a rounding, obviously. Well, that's a lot of work. And I'll just end this by just once again pointing out the difference between, maybe I should do that in red, not blue. The difference between, why are you not in red? There you go. The difference between cardinal directions, right? Those are your north, south, east, and west. And when we talk about degrees. Now remember, north on a compass is 0 degrees. But for trig, 0 degrees is over here due east. So that's why you can usually get into a second bit of trouble here, is if you don't wrap your heads around. what's going on. So once again, they gave us a nice friendly answer right here. Usually if you're looking at a meteorologist, they would say winds are coming from the southwest. And if they actually, like if you turn on a weather report and they actually gave you degrees, they wouldn't be giving you this degrees right here. They would be giving you degrees in terms of a compass direction right here, where 180 is directly due south. Okay. Luckily for us, we can take that all into account. So 225 on a compass direction is right here, but we know for us, north, south, east, and west, we know the difference between that compass and the coordinate plane system. All right. Hopefully that all made sense. And I believe that it's it for today. That was a challenging one right there. Once again, here's your homework. Good luck with that. I'll be here all day. I'll check my email a couple times. If we do have a snow day on Thursday, then I'll keep my computer on as well too. And email me if you need any help. And with that, we'll end it. Good luck.